All right, today is going to be lecture 17, and we're going to discuss something called inertial navigation. Let me go ahead and share my screen, and I'll pull up the course map. So this is just a reminder. Every time we change subjects, I like to bring up the course map just to make sure that we have a good lay of the land. So we spent the first chunk of the class on orbital mechanics, and then we spent the next chunk of the class on estimation theory. All of that is kind of the laying the foundation for the future work that we're doing. Then we spent a handful of lectures on triangulation and trilateration and essentially space to ground and ground to space navigation. So next we're going to be focusing on inertial navigation, which is this kind of gyroscope. So inside the spacecraft is a series of what are called inertial sensors, and we'll talk about those today, on how we can perform inertial navigation. There's only going to be one lecture on inertial navigation, and then after that, we're going to switch and talk about other, kind of onboard navigation techniques. It's going to be a lot of information about cameras and star trackers, and then about the flight computer and Kalman filtering. And then finally, towards the end, we'll talk about some of the pretty much brand new, like in the last decade or so, navigation techniques, like horizon-based optical navigation, terrain relative navigation, stuff like that. But for now, we are on inertial nav, and it's worth noting that this is the first lecture about autonomous navigation. So for the rest of the class, we're going to be talking about things that the spacecraft can do, even if there's nobody on Earth trying to help. Inertial navigation is a fully onboard system, and so is everything else that we're going to be going over. It's going to be all onboard systems, which I think is pretty neat. So this marks kind of a watershed moment for us. We're now talking about autonomous navigation as opposed to navigation that is done with Earth in the loop, or as opposed to any of the foundational stuff that we're going to be doing. So with that said, we'll start by talking about inertial navigation. So as a reminder, navigation. Oh, we have a question, or do we have a live mic?
Oh, sorry.
No, no worries. As a reminder, navigation from the first day means determining or estimating a vehicle's state. And in our class, we typically think of that as position, velocity, and attitude. Although there's other things, like there's clock biases that we might need to estimate as well. Navigation means determining a vehicle's state from available measurements. Yeah, I got to move the little box. There we go. From available measurements. So my question is, what can we measure in space? Can we measure in space? So imagine you are an astronaut floating around in your spacecraft. All of a sudden, you realize that you are lost. And what are our options? Well, I like to use the human body as kind of a metaphor for the spacecraft because we navigate real life with our body all the time. And you use your five senses. And really, there's more than five senses, but we'll focus on the main five senses. Which of those would work in space? So taste and smell are out. Hopefully, you're not tasting or smelling space. Something has gone wrong if you are. Those aren't going to be helpful. Hearing is also out because we can't get audio signals. But we can see things, which is going to be huge. And that could be light, could be optical, or it could also be radio waves, or it could be LIDAR. So light is going to be one of our best friends. And then there's your sense of touch, which if you're touching something in space, you better be expecting to be touching something in space, like maybe you're about to be coming in for a landing. But there's another human sense that we're going to be focusing on today, which is not classically one of the five senses, but you do have it. And if you didn't, you would fall over immediately. And that's going to be one of the things that spacecraft have as well. And so that is the human vestibular system, right? That is your inner ear, which stops you from falling over. Actually, I have kind of a quick anecdote for that, but let's see. So we'll just start with you can measure external things. So that would be, for example, light or radio waves, anything on the electromagnetic spectrum. And so think your eyes. But there's also internal measurements. and that would be essentially your rotation and your acceleration with respect to inertial space. And you don't need any external source to measure those. You can measure those all on your own, which I think is kind of neat. So think vestibular system or inner ear. So this is kind of well, you'll see. This is going to look like we're going off on a tangent, but it's going to loop back in. I remember when I was very small, I think I was less than 10 years old, my parents took me to the shopping mall one day and we got a toy that I was very excited to go home and play with. I don't even remember what the toy was, but I remember that I was very excited to go home and play with this toy and that it's not one that you can play with in the car. You kind of have to be back at your house. And I was very excited and we hit a traffic jam on the way home from the shopping mall, and I was just losing it because I was so desperate to go home and play with this toy, and I was just like, it's all of the normal frustration that you have with a traffic jam, combined with really, really wanting to be home, combined with being less than 10, and so your emotions are just 0 to 60 really quick. So I was very frustrated with this traffic jam. And at one point, and maybe this is just the way a kid's brain work, I was like, I know, I'm just going to close my eyes and try to forget that I'm in a traffic jam, right? I'm going to, and then maybe, who knows, like maybe, while I'm not paying attention, the traffic jam will up and we'll be halfway home by the time I open my eyes. I think it's the same weird logic behind pretending not to pay attention to your phone while it's buffering, because maybe it'll go a little bit faster at loading the video or whatever it is. But that was my logic at like 8 or 9 years old. And I very quickly realized that that wouldn't work because if you're in a car with your eyes closed, you still know when you're moving and when you're not moving. And you could test this, although I would encourage you to get a friend and don't be driving when you're doing this. But if you're in a car with your eyes closed, you know when you're turning, you know when you're driving straight, you know when you're speeding up, you know when you're slowing down, you know when you're going at a constant speed, you know when you're stopped. You know all of those things, even if you were completely blind and deaf, because you can feel it with your body. You can feel it. You can tell your orientation with your inner ear. Mostly what you're feeling is sensed acceleration of the car, essentially. Speeding up, slowing down, going around a turn. And you can also use your equivalent of your vestibular system to determine the orientation of the spacecraft with respect to inertial space. And you don't need any external measurements to do that, which I think is kind of cool. So to write that down in note form, if you were in a car with your eyes closed, and then in parentheses, don't do this while driving, you could feel the rotation and acceleration of the car. And so essentially you can still tell that you're upright. Actually, in the early days of aviation, so nowadays there's instruments in an airplane that can tell you your attitude and your heading and all sorts of other information. But you can also tell when you're turning and when you're, flying level and when you're same ideas, because you can feel the airplane essentially with your back and with your butt, the part of you that's touching the airplane. And that's where the phrase flying by the seat of your pants comes from. It's like, flying by the seat of your pants means that you're not using any instruments, you're just going entirely by feel. I think flying by the seat of your pants was the 1940s version of no numbers, only vibes, basically, was what that phrase means. And so, yeah, that's the idea behind inertial navigation. And so you might be saying, well, if we can do that for the human body, why not do this for aircraft and spacecraft? And another one that comes to mind is submarines. And the answer is that we do. We do that for aircraft, spacecraft, and submarines. Inertial navigation is indispensable for aircraft, spacecraft, and submarines, and others as well, but those are the ones that immediately come to mind. So you might be wondering how it is that a submarine, or maybe you don't think about this very often, but this is something that's come to my mind. How is it that a submarine can go under the water in a location and then surface in another location exactly? How does it do that? When it's down there, it doesn't have GPS. There's no GPS. It can't take really any external measurements of its surroundings. It can get its depth from a pressure sensor, which is great, but how does it know its like XYZ location? And the answer is it knew what its XYZ location was when it went under the water, and then it felt every push of the water on the ship and recorded all of them and then integrated them together. And now it knows where it is going to be surfacing. And that's inertial navigation. Now, you might say, oh, this sounds fantastic. Why do we need other forms of navigation? Well, inertial navigation is not perfect, right? There's going to be problems with the sensor. There's going to be issues with integrating. A great inertial navigation system will have about 1% error. So if you travel 100 kilometers, you'll be off in your position estimate by 1 kilometer. That would be a fantastic inertial navigation system. So there is a sensor on a lot of spacecraft, which we'll get into now, called oh, hang on, stray mark, there we are, an inertial measurement unit, or IMU, is a sensor suite that takes inertial measurements. I'm going to abbreviate measurements that can be used for navigation. And then it might follow naturally that navigation that is done using these measurements is called inertial navigation. Not internal navigation, as you might be thinking, because you can think of these as internal measurements, right? You're not looking outside the spacecraft for information about acceleration and rotation, but you are measuring acceleration and rotation with respect to inertial space, which is not rotating and not accelerating. So it is inertial navigation, not internal navigation. So an IMU consists of accelerometers and gyroscopes packaged together. So the gyroscopes are good for sensing your rotation, and the accelerometers are good for measuring what I'm going to call felt acceleration. We'll talk a little bit about what I mean by that later. So questions up to this point? So far, so good? All right. The next bit is a short little history lesson, which I really love this story. I think this is a fun story. You might be familiar with this. Some of you who are huge navigation geeks might have read about this already. In February 1953, a B-29 Super Fortress, that's a type of aircraft. Oh, hang on, not Fortress, but Super Fortress. Took off from a town called Bedford, Massachusetts, and flew to Los Angeles International Airport, LAX. It flew the entire 3,000-mile journey with no input from either pilot. The pilots had their hands off the controls. You might be saying, well, that's not so impressive. Why don't you just use autopilot? I'm like, that's what this is. This was the first autopilot. It flew the entire 3,000-mile journey with no input from either pilot. And was less than 10 miles off. Of course, by the end. So this was the first autopilot. So rather than a human, control was given to a washing machine sized inertial measurement unit. Nowadays, you have an inertial measurement unit in your cell phone. Let's see, it was given to a washing machine sized IMU and a flight computer. This IMU was developed by a company that might sound a little familiar. It's called the MIT Instrumentation Laboratory. So yes, the RPI Instrumentation Laboratory is a tongue-in-cheek reference to this company. And on board was the head of the MIT Instrumentation Laboratory, Dr. Charles Stark Draper. And some of you are thinking, hey, Draper sounds familiar. Yes, that Draper. Yes. If the name Draper sounds familiar, that's why. So the company that was MIT Instrumentation Laboratory was eventually renamed to Draper Laboratory. And Draper is still a company today. I did an internship there as a grad student. It's a great company. I have friends that work there. Charles Stark Draper was on his way, and this is he gets a lot of credit for this. He was on his way to a conference in Los Angeles to discuss if inertial navigation would ever be practical. So yeah, this Draper was something of a showman. He was going to a conference on whether or not inertial navigation was something that we should be pursuing. Should we be trying to put inertial autopilots on aircraft? Is that a good idea? What do we think? And Draper arrived and just turned around and said, "Yep, I landed on a plane that got here with inertial navigation." Just blew everybody out of the water. And this same technology, and these people, the same company, Draper Labs, were instrumental to the success of Apollo. So this is the same company that made the Apollo guidance computer. This is the same company that made the computer programs that went on the guidance computer. They made the inertial navigation system. They made the space sextant and essentially the early form of a star tracker. The people who were at the MIT Instrumentation Laboratory worked on something that was not hardware. It was programs that they fed onto a computer that was going to command the hardware. And people at first jokingly referred to it as software. So the name software comes from the MIT Instrumentation Laboratory and the rush for Apollo. So I just like to spend a little bit of time on history. This really has nothing to do with, our navigation needs right now, but I think it's important to know where we came from. So back to more practical matters. Platform, there's two types of IMUs. Platform IMUs, like the ones that flew on Apollo, relied on a gimbaled platform. To isolate sensors from the rotation of the spacecraft. So you can imagine if we go back to our map of the class, inertial navigation is depicted with this kind of three-axis gyroscope, right? That's the idea. Gyroscopes do not need to look like this, but the earliest ones did. It was essentially sensors on a ring, which could rotate about another ring, which could rotate about another ring, which could rotate about another ring. And this series of 3 rings on Apollo or 4 rings on Gemini were sufficient to isolate the sensors from the rest of the spacecraft. So you can imagine you've got a platform that isn't moving with respect to inertial space. As you rotate around, it maintains its position. And then you can just read off the angles from the gimbal to give you your orientation. And then similarly, you can get your acceleration along the line of sight direction, or along the directions that the sensor is mounted. So platform IMUs require this gimbaled platform. There are more modern IMUs, which are called strap-down IMUs. So strap-down IMUs, which are more modern, rotate with the vehicle. And so you could think of it this way. Angular velocity is constant throughout a rigid body. So it doesn't really matter where you measure it. But angular acceleration is not. So this drives the placement of strap-down IMUs. You generally want your IMU to be close to the vehicle's center of mass, but you're never really going to be able to achieve that in practice. So you need to account for the offset in your equations, which we're going to kind of gloss over that today. We're going to focus more on a gyroscope and accelerometer error model. That's mostly what we're going to talk about today. So we're going to start by talking about gyroscopes. Questions on any of this introductory stuff so far? All right, cool stuff. So gyroscopes, or I'll often abbreviate these to just gyros, measure the inertial rotation of the sensor frame. And so I kind of alluded to this already, but there are mechanical gyros. Think Apollo era. Consist of an inertially stabilized platform connected to the spacecraft by a gimbal. And those gimbal angles basically tell you the orientation of the spacecraft, because in theory, the mechanical gyro doesn't move over the course of the entire mission. Now, in real life, it does, and we need to account for that. And so we also have more modern optical gyros. Like you can imagine the name optical might make you think of light, and that's exactly it. Optical gyros, oh, apologies, I skipped a word, like the ring laser gyro, which sounds really cool. That's the RLG. And the fiber optics gyro, FOG, are used in high performance spacecraft today. Then there's also a third type of gyro, which also sounds pretty cool. It's called a Coriolis vibratory gyro. So CVG are smaller, cheaper, less accurate, and are used in smartphones. So you've been walking around with an inertial measurement unit all day today. You might not have known about it. Because you might wonder, how does my phone know when I've tipped it over? Well, it's got a CVG. It knows when it's been tipped over. It knows to make your video full screen because you have your phone on its side now because of a Coriolis vibratory gyro. CVGs are also used in virtual reality environments, like the one that I was in earlier today, where you've got your left and right hand controller, which seem to know their orientation and position with respect to your head, such that when you hold your hands out in front of you in virtual reality, they really are where they seem like they are, or I should say, they seem like they are where they actually are. And that's also because of inertial navigation and IMUs. So we're going to focus on optical gyros because those are the ones that are most likely to be on your spacecraft. So optical gyros. Actually, I just realized my pen tablet that I'm using to write these notes right now probably also has some sort of IMU on there. Optical gyros operate on something called the Sagnac effect. And it's possible that that is pronounced in a cool French sounding way. I've only read that word, which is itself a consequence of general relativity. So here's the idea. A beam of light is split and travels in opposite directions around a circular path. If that path is rotating, the light will have a longer path to travel in one direction. And so essentially there's a sensor that catches the light from both beams and measures the phase difference. And we're not going to go into the math, basically the relationship between the phase difference and the angular velocity, but that is something that you could look into if you were curious about. For now, we're just going to say this is how this works and then move on. Coriolis vibratory gyros, CVGs, by contrast, measure the force required to rotate a vibrating object. So as a note, vibrating objects tend to want to keep vibrating. To vibrate in the same plane. And so if you rotate a vibrating object, it will produce a Coriolis acceleration. And that's ultimately what we're measuring with the CVG. So rotating a vibrating object produces a detectable Coriolis acceleration. So there's a little bit about how your smartphone's CVG works, and then also how a spacecraft optical gyro works. So with that said, our next discussion is going to be on error sources, because you will not in this class, this is not going to be on the homework, but you might at some point in the future need to put together a sensor model for an IMU and say, well, look, here's reality, right? We like sensor models in this class. Here's the real physics describing the situation that's happening, and then here's what you're going to measure as a function of those physics. And what's that going to look like? And so that's what we're going to explore next. But I'll pause here if anybody has any questions about gyroscopes. Otherwise, we'll keep moving. All right. So next we're going to talk about strap down gyro error sources. All right. So there are 5 that we're going to be talking about in this class. The first is scale factor error. So scale factor error is conversion from voltage to digital number to engineering units. What are the odds that that's going to be perfect, right? So imagine that your CVG or your ring laser gyro ultimately produces a voltage, and that voltage is related to your angular velocity in radians per second. Well, just the conversion from a voltage to a number that's a digital number, like typically 8-bit or 12-bit, 16-bit, and then ultimately to an engineering unit, there's going to be some error there, so some scale factor error. There's also going to be misalignment error. So you have a gyroscope mounted in your spacecraft. How is it mounted? Exactly. Because the probability that it's mounted exactly the way that you said it was is 0, right? Nobody's perfect when they're assembling a spacecraft. So the attitude of the sensor, or the sensor frame, I should say, with respect to the spacecraft frame is slightly off. No matter how good your technician is, they're not going to get it perfect. There's also something called non-orthogonality error. So we'll typically have 3 gyros. You'll have one to measure your angular rotation about the x-axis, one about the y-axis, one about the z-axis, all working together. What are the odds that you have mounted those in the spacecraft perfectly orthogonally? So not only are they not going to be mounted correct in an absolute sense, they're not going to be mounted correct in a relative sense. There's going to be, even if it's 4 arc seconds, like a 60th of a 60th of a degree, tiny, tiny amount of error, it's still error, and it's still something that we want to build into our error model. So this is orthogonality error. So the gyros, there are 3 of them, were not mounted perfectly orthogonally. Let me clear up that stray mark there, and then we'll keep moving. Oh, I lost the letter O. Let's fix that too. All right, on to the next one is sensor bias. And so that one is, as the name suggests, some offset in the measured body rate. And then there's also something called readout error, which is essentially just sensor noise. So readout error is just noise in gyro output. And so we can use these to put together a gyro error model. So here comes our gyro error model. All right. So we will begin with only readout, error, and bias. So if you, knowing what you know now, and knowing that these are the 5 things that we're going to try to measure in strap down error sources, you might say, okay, well, look, probably the angular velocity, so we use omega for angular velocity, and it is a vector, and then we've got the squiggle, which this is the measured angular velocity. Well, knowing what we know in this class, it's going to be the true angular velocity plus some noise, right? Well, really, it's going to be the true angular velocity plus some bias plus some noise, where the bias is some number, which actually is subject to change over time. But you're going to be saying, well, you know, let's say that the true angular velocity is exactly 3 radians per second, but your sensor just runs fast, and so it's going to return 3.01. That's a 0.01 radian per second bias that's there no matter what. And then you've just got your noise on top of that, and that's going to be your random number with 0 mean and some standard deviation, right? So we're kind of used to the bias and the noise from our discussion of estimation theory. But just to be very clear about everything we're seeing here, this term is noise. This is your bias. This is the true body rate. And this is the measured, other way. This is the measurement, or the measured rate, where the Greek letter nu, I should be clear, the expected value of nu transpose is, we're going to call it sigma v squared I 3/3. Right? So this is the measurement covariance matrix. This is specifically the noise on our measurement follows this covariance. That's going to be how we model that. So what we have right here, this kind of simplest possible gyro error model, is called the Fahrenkopf gyro model. So this has a name. This is the KOPF gyro model. The simplest used in aerospace applications. So if you're not accounting for at least bias and noise, you've done something wrong. But there's more, right? We should be clear here also, we do not treat the bias as a constant. Rather, we model it as something that you might have heard of before, maybe not, a first order Gauss-Markov process. That's often abbreviated as FOGM, first order Gauss-Markov process. What the heck is that? So imagine that you've got your sensor bias. We don't want to treat that as constant over time, because actually the bias itself has its own noise. So just imagine, and you don't need to write this in your notes, imagine that you were going to be graphing your bias as a function of time. What we're looking for is some kind of wiggly line, basically. Going to be some wiggly line. And we can parameterize that line, which is what we're going to do now. So here's a first order Gauss-Markov process. They follow this differential equation. B dot is equal to negative 1 over tau b plus eta, where tau is correlation time and eta is white noise. So zero mean Gaussian noise. So there's noise on the measurement, there's also noise on the bias. And you can think of it this way. If your bias, if the derivative of your bias, so your bias is starting off at some number, and then its derivative is negative 1 over tau of itself plus some white noise. If we imagine for a moment that we ignored the first term, if the derivative of bias was a completely random number, then this would be something that we call random walk. So you're starting with a random number, and then its derivative is completely random. Well, it's just going to wander all over the place. There's going to be no rhyme or reason to it. The first term, negative 1 over tau beta, is basically a return to normal. So the random walk is going to want to make it just wiggle all over the place. And this negative 1 over tau beta, well, what is something where if x dot is equal to, I don't know, negative x, right? That's going to be a nice, simple exponential decay. And so the combination of this exponential decay and this kind of random walk gives us this wiggly line, which likes to wander around, but ultimately ends up kind of starting off where it, or ending up where it started. So we will talk about the first order Gauss-Markov process again later in this class. For now, this is pretty much all the depth that we need to go into. So we've covered bias and noise. What about misalignment error? Okay, so we model that as a small rotation. Okay, so now our equation is going to look like this. Omega with a squiggle, meaning this is our measurement, is some delta t, this is our small rotation, times the original omega, plus our bias, plus our noise. You might be thinking, shouldn't delta t apply to everything, or should it only apply to the original omega? Well, the idea here is that, and I'll put this in parentheses, bias and noise they have everything to do with the sensor electronics and nothing to do with how it's actually mounted. So we don't care about them when we're doing our rotation. We just rotate the actual true value. Bias and noise have to do with sensor electronics. Therefore, they are not affected by rotation. All right. Now we can actually clean this up a little bit. If the matrix delta t corresponds to the angle vector delta phi, then we can do a fun trick. So as a reminder, T is our attitude transformation matrix. We learned about that. We're pretty confident with those at this point. Phi is our angle vector, right? So the direction of the vector is the direction that we're rotating about, and then the magnitude of the vector is the amount that we're rotating. So theta and E multiplied together gives you phi, and we're saying delta phi. So this is a very small rotation. Well, then if that's the case, then there's a fun little trick that you might like to use. Delta t is approximately equal to the identity matrix minus delta phi turned into a cross product matrix. And we're just going to clean this up and say, well, delta t is equal to I plus E, where E is just defined as negative delta phi cross. So it's a new matrix we're calling E. Right? And so we can clean this up a little bit further, and you'll see why we're going to do this in a minute. Now we can say that our angular rotation, or our measured angular velocity, is the identity matrix plus this matrix E, which has to do with our misalignment, times the true omega plus a bias plus some noise. All right. Next, we've got, so let's scroll up. How far along are we? We've got the readout error, we've got the sensor error, and we've got misalignment. Next, we're going to handle non-orthogonality. So, likewise, we can account for non-orthogonality with the transformation. Oh, I didn't mean for my handwriting to kind of arc up like that, sorry. Non-orthogonality with the transformation delta G. We want to be clear which is not proper orthogonal. So this is not a rotation. This is something else. So it's going to look like this. Delta G is approximately equal to the identity matrix plus capital gamma, where gamma is this lower diagonal matrix, which looks like gamma 1, gamma 2, gamma 3. So this lower diagonal matrix being multiplied together with our other terms is what produces this effect where you might imagine in a perfect world, we've got X, Y, Z, but in our world, it's ever so slightly not perfectly orthogonal to one another. It doesn't exactly follow the right-hand rule. This is how we model that. That's essentially the idea. And so in this case, what this would give us is that omega is equal to I plus gamma, I plus E times omega plus bias plus noise. Where again, bias and noise have everything to do with the electronics. They've got nothing to do with the non-orthogonality of the sensor. So we're going to leave them out of this for now. Finally, and we can take a break soon because we've been going for a little while, we account for scale factor error by scaling the output. And we scale the entire output by some amount, which we're going to call I plus S. I is, again, the identity matrix, where S is some diagonal matrix, which we'll say is Sx, Sy, Sz, 0, 0, 0, 0, 0, 0. There we are. So there's a scaling in the X, a scaling in the Y, a scaling in the Z. And this only is going to apply to the bias and the noise, because now what we're doing is we're taking the electrical signal and converting it to an actual, radians per second measurement. So this gives us our full gyro model, which looks like this. Omega squiggly, so this is the measured, is I plus S, open brackets, I plus gamma, I plus E, actual angular velocity, plus bias, plus noise. There we are. Now this is a bit much, so we're going to simplify this a tiny bit. If we assume, hopefully this is true, that all errors are small, so we're pretty close to being orthogonal, we're pretty close to being mounted in the correct direction, and our readout error or our scale factor error is very small. If we assume that our errors are small and we keep only the first order terms, then it simplifies to this, and this is going to be the equation that we walk away with. So omega is equal to I plus S plus gamma plus E, all in parentheses, omega plus B plus V. That's correct to first order. And so we have some error terms. So just as a reminder, we're going to have our whole cast come out and take a bow. The error terms are SX, SY, SZ, gamma 1, gamma 2, gamma 3, and delta phi, which is itself a vector. I should actually make that clear. Let me scroll up. This is a vector. So there's 3 measurements. That's 9 total error terms. These are calibrated on the ground before flight. Actually, well, that's probably enough on that for now. And then the bias is estimated as another state. And there we are. So there's our full discussion on the gyro error model. And actually, I'm wondering, do we want to take a break right now? We've got about between 5 and 10 minutes worth of notes on accelerometers, and then we're done. So I'm kind of feeling like maybe we should just power through and finish up our discussion. This is a rather shorter lecture today, so it's going to be about an hour total. Yeah, with your permission, we're just going to keep on moving. But if y'all need to drop off for a little bit, you can always come back and watch the video after it's posted. We're going to talk very briefly about accelerometers. There is one very clear point that I want to make about accelerometers that is important to remember. Accelerometers. Okay. Accelerometers measure what I'm going to call sensed acceleration, sometimes called felt acceleration. Basically, when the vehicle is pushed. So going back to the analogy of when you're in a traffic jam, you can feel with your body whether or not the car is moving because you can feel with your body when the car is pushing against you. If hypothetically, and don't try this at home, you were to drive the car off a cliff, and again, don't try this at home, while you were in free fall, you would be floating. And let's say that there's a trampoline at the bottom of the hill, so this doesn't get too morbid. On your way down to the trampoline, you would not feel any acceleration. Your internal accelerometer would give you no data. So similarly, if you're on a spacecraft and you're just drifting, your accelerometer is giving you no data. This is why some folks who come from a robotics background are tempted to say, well, look, we have an inertial measurement unit on board. We should be good to go, right? Because a submarine or an aircraft that has its IMU is constantly recording the pressure on the IMU. But the thing is that the submarine and the aircraft are flying, not floating. You could think of it as the submarine flies through the sea, the aircraft flies through the air, but the spacecraft is truly just drifting, right? And because it's drifting, its accelerometers are not useful all the time. Its gyroscopes are useful all the time. Its accelerometers are not. So there's a very clear point that I want to make. Accelerometers only provide useful data when an external force acts on the spacecraft. Just want to clear up a misconception. Only provide useful data when an external force acts on the spacecraft. To be clear, gravity is not an external force because it affects the sensor and the spacecraft together. So going back to the metaphor of the inner ear, right? So you have a gyroscope and an accelerometer in your inner ear, essentially. if you are, actually, that might not be the best possible example. So, a better way to think about it is if you're drifting around in space, then there's no feeling of gravity. You can't feel the gravity. When you're sitting in a chair, you feel the earth pushing up on your feet and on your butt, and you can tell that you're sitting in a chair, and you know that you haven't fallen out of the chair, and you know that even if your eyes are closed. But in space, if you start off in a chair and then you just drift out of the chair and you kind of start twisting all over the place, it's going to be very difficult to tell that you've drifted away because the sensor, like the accelerometer, and the spacecraft are all moving together. Really, what happens is if you push on a spacecraft, the spacecraft then needs to push on the accelerometer to get it moving, and that's what does the sensing essentially. But if they're both being affected the same way by a remote force like gravity, it won't take. So it might sound like I'm hammering this on pretty hard, but I really want to make it very clear. Accelerometers are useful during, for example, a burn when you light your engines or orbital maneuver. Is an external force. So the way I like to put it is this: accelerometers are only useful for navigation whenever the crew would need to buckle their seatbelts. So when, for example, the International Space Station is burning to raise its orbit, then the crew actually does visibly move on the station. They actually need to grab something, or they need to kind of plan their day around that. And during that period of time, any accelerometers on the ship would actually be able to pick up its motion. But when it's just drifting, it won't be able to pick it up. Accelerometers are not mounted at the center of mass of a vehicle because that's impossible, right? The true center of mass is always moving. Even if your fuel sloshes a little bit, you've moved your center of mass. Accelerometers are not mounted at the center of mass of a vehicle because that's impossible. Therefore, they measure angular and translational acceleration. So we do need to account for that. Fundamentally, accelerometers, this is kind of what I was alluding to before. Accelerometers work by measuring force. They measure the force required to accelerate a proof mass. So a mass its mass is very well known. So same idea. The something pushes on the spacecraft pushes on the accelerometer, and that push is felt and turned into an electric signal. So this all works off of Newton's second law. So one or two more equations. The total acceleration on a vehicle is this. The acceleration acting on the spacecraft, which is total, is the acceleration due to gravity plus the acceleration that would be measured by an IMU. So this is measured, this is due to gravity, and this is total. We can use a mathematical model to estimate gravitational acceleration. That should sound a little bit familiar, right? We've already said, and don't write this equation down, that r double dot is equal to negative mu r over r cubed, right? That is the two-body mathematical model. Then there's three-body, and there's n-body, and there's taking into account gravitational perturbations, and there's all sorts of other stuff. So if you have a very high fidelity understanding of where you are and where everything else is, you can put together a model of what your acceleration ought to be. And so we do that. But then you also can measure what is felt on the spacecraft. So the basic error sources on an accelerometer are the same as on a gyroscope. So even though we're measuring something translational instead of rotational, there's still non-orthogonality and scale factor error and bias and noise and all that other stuff. So the basic error sources for an accelerometer are the same as for a gyroscope. And so as a reminder, those are scale factor error, misalignment, non-orthogonality, bias, and readout error. All right. So thus, not shockingly, the measurement model is of the same form. So the accelerometer IMU as measured is I plus S plus gamma plus E times the actual IMU acceleration plus your bias plus your noise. There we go. And those are all the notes that I have for y'all on inertial navigation. So we've been going at it for just a little bit over an hour. I'm going to stop for a minute. I'm going to stop the recording. I'm going to stick around for as long as people need to answer questions about homework 3. I'm going to go ahead and stop the recording. And y'all are free. If you want to take a break, because I know we've been going at it for about an hour, I'm not going anywhere in the first 5 minutes after we leave. So really, in whatever order you want to do this. But I'm going to go ahead and stop the recording. For anybody that feels content and they're good on homework 3, then class is dismissed. I hope you all have a fantastic weekend. Hope you have a great spring break, and I'll see you back here. We're going to start talking about star trackers on the next lecture. So thanks for coming, everybody.